Yeah, let's go.
All right, welcome to Reverse Engineering 2.
There you go.
So announcements, tomorrow night, we have pizza and game night. It's like a social, just like, it's gonna be in Siebel in room 2406 at 7. So just show up, we're gonna be playing games, eating pizza, watching movies, It's gonna be fun. It's a great chance to meet new people and say hi to like people who you might not have seen in the club before. And then here's the meeting flag and the meme of today's meeting. I'll give you guys a minute to like type it in on the SIGPwny CTF. Okay. So for this meeting, we'll be using Ghidra for like the demo at the end of it. So if you haven't installed it yet, download it through the slides that are linked here. The slides are also linked on the SIGPwny website. So you can scroll down a little bit. They are.
Oh, I'm working on uploading the current slides, but the rev setup slides should be up.
Oh, okay, yeah. So the rev setup slides are uploaded on the website. These ones will be uploaded in a little bit.
Yeah, just type in the link. If you
Yeah.
haven't done. So we got a Rev 1 meeting. Can you raise your hand if you went to it? I mean, it's not really relevant, but. Right. So this meeting is a continuation on that before compiled further. So reverse engineering generally is trying to figure out how a program works and getting some information out of it. The reason we care about this is because if you're hacking programs out in the wild, they're often not going to give you the source code, they're just going to give you the binary. And sometimes you still need to get information about the program just from the binary. Now, it turns out there's ways to do it, even for compiled programs. So that's why we care about it. You should care about it also because if you're able to reverse engineer programs, you have to have a good understanding of like the whole level of programming, from how the CPU works to how low-level programming languages work. So what's actually happening with your source code to the compiled code. You get to learn about every step in between. So I think it's worth learning even if you're not going to do hacking professionally. And then the two techniques are static analysis, which we're going to do with Ghidra, and dynamic analysis, which we're going to do with GDB, which you'll see more about.
All right, so before we start with actually debugging or analyzing the code, we're going to do a recap assembly. So how many of you guys were there at the assembly meeting last Sunday?
It was awesome, right?
Yeah, it was a great meeting. So Julius got there presented. Yeah. Okay, so what is assembly? Assembly is basically but like what we use to understand machine code better. So machine code is just a bunch of numbers, looks like that. And so this is what computers use, like when they give the instructions to like a CPU. But we can't like remember all the numbers that for like every single instruction, because there's so many different types. So what we can do is use assembly. And so assembly is just like these numbers turned into like something that we can use. And so, yeah, that's what this is right here. So on the left here, you can see a simple C program. And so what this is doing is just taking in like an input, and then it's returning 6 plus like that input. And so if you look at the assembly, you can see that it's a lot longer. It's obviously easier to program in a language like C, but the assembly is what the C gets turned into through like a compiler. And if you use like a language like Python, which is interpreted, then eventually that will also get turned into machine code that the CPU runs. So basic CPU structure, we have instruction memory, so that is the actual memory that contains like instructions that the CPU will run. So in this case, this assembly right here will be turned into machine code, so like a bunch of those numbers that you saw earlier. And so that is what the CPU will run. And these are stored in memory. So like in different locations of like your RAM, for example. And then you have registers, which is what your CPU can use to like store different data. And so you can think of registers like variables in like a C program. But these registers are actually like hardware. You can actually put like bytes in them in hardware. And then we have our runtime stack. And so the runtime stack is basically how the computer can keep track of different variables when it's executing a program. So maybe you're executing a new function, and this function has local variables. So what happens when the computer executes your program is that those local variables get pushed onto the stack. Like, for example, maybe these two get pushed onto the stack. And so then your computer can have those variables in memory so they can find them later. And so maybe when we perform an operation and like add those two values in memory together, then we can pop those values and get rid of them from the stack when the function's over. So what is this meeting about? This meeting is about reverse engineering binary files. And so these are the kinds of files you would see if you were hacking a program. You can have like source code. You'd see like a compiled file, and you'd have to somehow extract data out of it. So what do we have to work with when we find these kinds of files? We have machine code. So that's obviously all those numbers that the computer sees. And then we have symbol names. So in assembly files, you can have labels that like point to different like I guess areas of the file. And so we can access those labels. But basically, what we can see is what the OS needs to see to execute the program. It's nothing more. You shouldn't expect any more when you're hacking a program, because why would they give you anything more than like what the OS needs? So otherwise, that's an easier way to like for hackers to get into programming. So this is an example of what you put in a command prompt when you're trying to debug a program. So let's just say debugger is your binary file that you're trying to execute, and you want to see if this is like the right flag. That would like say you're simply this flag. So you can execute this dot slash just executing that debugger executable, and then this is going to be your input. And so from putting in this test flag, we don't really know what's going on behind the scenes, right? It's all it says is this flag is incorrect, and we wouldn't ever know how to get the right flag out of this. But by the end of this meeting, you'll be able to find what the flag is. So what is the ELF format? ELF stands for executable and linkable format. And so what this is, it's basically, if you look here, you can see the type of file that like the debugger executable is. And it basically contains the program code and any additional data that you might need to execute the program. It can also contain the symbols that I was talking about earlier, the symbols in like your assembly file. And if you'd like more info about this, you can look at this file. When we upload the slides, you can click on that link and check out that GitHub. And a useful tool to use when you're working with ELF files or like an executable in that format is readelf. So how does like some source code that you wrote in like C or C++, maybe Python, actually not Python, C or C++, like how does that turn into an executable? So what we do is, you guys might have worked with this before, but you can use Clang or GCC, basically a compiler, that turns your code into machine code, or into assembly. And so this compiler, will like optimize your code, whatever, read through your code, go through it. And it turns into assembly, and then from there, an assembler will take that code and turn it into machine code. And if you have multiple files, a linker will like link everything together, but we don't have to worry about that for now. But we can also go the other way. So for example, if we have an executable, which is what like when you click on like an application here, it's an executable. So if you want to go the other way, we can turn that into assembly and turn that to source code. But the big question is how, because that's like a complicated process, right? So we have,
Okay.
so we have disassembler, and so this step is pretty easy, compared to like the next step. But what it does is, it can take these binary bytes, or like you can see on the left here, it's kind of in a weird color, but you can take that and turn it into assembly. If you know what operating system, or like architecture, not operating system, what architecture the executable is made for, you can find out what assembly instructions those values would correspond to. So that's how we get to the assembly step. But then how do we get to the source code from assembly? So this is where a decompiler comes in. And that is what Cameron will be talking to you guys about.
So as we said, going from machine code to assembly is easy. It's mostly a one-to-one transformation both ways. So whenever you get a machine code, you can mostly recover the original assembly. But going from assembly to the source code in C or something that's human readable even is difficult. But thankfully we have tools that can help. So yeah, here's an example of going from C to assembly on this website called Kabbur.org. So it like color codes it so you can see what parts of the C code correspond to what parts of the assembly. And that can help you get a sense for how your C is being transformed into assembly by the compiler. So here's your challenge. You have like 10 seconds. Because it's not actually that important that you can figure this out. All right, does anyone have any guess of what the corresponding C code may look like? And the answer is probably like, I have no idea. What does L3 imply? Some people, if you've taken a SIGPwny or some other class that has you write assembly, you might have some suspicion that there's a loop somewhere in there because we're doing these compares and jumps, but the specifics seem pretty obscure. As it turns out, yeah, there's a for loop, and it's just adding numbers and then returning the result. But as you can see, reading the assembly was pretty hard. It takes some thinking. So even though like we talked about how people have written these huge programs in assembly, like Roller Coaster Tycoon, that's pretty different. That's usually human written assembly that's meant to be human readable and it's well documented and the author knows everything about it. This is not that. This is compiler produced code that is very hard to read. So that's why we've invented tools to help through it. And Ghidra is the one that we're going to teach you how to use. Raise your hand if you've used a decompiler other than Ghidra. Yeah, okay, good. Because we're only going to show you Ghidra. Yeah. So yeah, Ghidra is open source written by the NSA, and it helps you convert binary machine code to the pseudo C, and we'll explain what pseudo C means, but it helps you just take the binary code and get it into a sort of human readable format. It often takes some work for it to actually be human readable, but it's a lot better than the raw assembly we were looking at earlier. And again, as I talked about, compiling, so the process of taking C source code and getting a binary is often non-recoverable. So even though you have the compiled bytecode, or sorry, the compiled machine code, you won't always be able to return back the original C code perfectly. And compilers make it even worse by adding in optimizations, which Ghidra will get confused by sometimes, and you can see here the code that Ghidra generates looks pretty different than the original code, and this might be pretty hard to actually read what's going on, whereas this is like super easy to read what's going on. So again, it might take some work on your part to understand Ghidra's output. And what I meant by pseudo C is that it is often not recompilable, so it's often not actually valid C. So even though you can read it, you often can't compile it, so you won't be able to run your Ghidra output either. So yeah, the goal is just so that you can kind of understand what's going on and maybe recreate it in a different language or recreate it in C once you figure out what actually is happening. So yeah, I was talking about these optimizations. Here's one where you'll often see this in your Ghidra output. So we have this char array. And you can see we wrote out the underlying specifiers for the char array. But in the Ghidra output, you just see like a local variable being assigned to this super long hex number. But the reason why is that it's loading like the first 8 bytes from the string to a register, and then it's doing it for the rest of the string. And then you can see though that there is some sort of correspondence, like the 6F here corresponds to the 6F here, the 7-7 here corresponds to the 7-7 here. But can anyone answer me why is it backwards? Like, why they're reading from the end of the 8 bytes?
NDNS.
Yeah, I'm trying to explain.
Well, like the NDN, it'd be like your actual binary would be like in order of your actual numbers, and then there's got thing called little NDNS, which like a lot of like reduced instruction sets used too, and it's like your numbers go in reverse. So like you can see there, like the hex is actually just reversed from what the actual like numbers.
Yeah, that's right. So the order goes from the least significant bit heading towards the most significant bit. So the start of the string is actually at the end of the number. And yeah, you said that because x86-64 is little endian. It doesn't really matter. You don't really know how to like understand why, but if you see this in your Ghidra output, just know like, hey, this could be a string. And we'll teach you how to get Ghidra to interpret it the way you want it to. And here's another common optimization you'll see is you'll see these kind of weird bit masks in your Ghidra output. So that corresponds to modulo. And can you ask me what specific, like this doesn't work for every modulo or every modulus. Like what types of modulus does this trick work for that you can replace it with a bit mask? Yep, it's power of 2. But that's pretty common to see for a modulus anyways. So I'm not going to talk about what all this is, but once the slides are up, you'll be able to, yeah.
A question on the previous slide.
Mhm.
So sometimes they'll optimize using a bit mask. Like sometimes they'll optimize using modulo for what reason?
I mean, like you can think like a modulus involves dividing, right? But a bit mask, but this is just an AND operation that can be like one cycle in your CPU model. So like, this is way faster than doing a division. So that's why they optimize it like that. So yeah, that's a compiler optimization. So like it's not Ghidra. Ghidra is just telling you what the machine code looks like. Like it actually got added in the compile step. Yeah, I'm not going to talk about these, but you can refer back to when you're solving shells. I can do this. Okay. All right. So GDB is the dynamic analysis part. So everything we're talking about, you can do without actually being able to run the program, which raise your hand if you have a Mac. That's gonna be fun for you because running these programs that are compiled for Linux will require Docker, especially if it's compiled for x86-64, which we're teaching you. Some of your guys' computers will actually be running like ARM, which will make things even more complicated, but Docker will help you. I have a slide trying to tell you how to do that, and then I'm working on this, but it'll be tough. Yeah. Dynamic analysis is, I think you can kind of see it's only useful because you'll be able to see the state of your program as it's running. So if you have this long, complicated, or this long, complicated piece of code, at the end, it computes a value and stores it into a variable. You could set a breakpoint and then just print out the variable. So raise your hand if you've used GDB. You know, if you've taken a more advanced CS class, you might be forced to use it. Some of you? All right.
I think it's introduced in 128.
They continuously reintroduce it in like every CS class, like 128, then 225. And the first time I think I really used GDB was 341. So
Yeah.
it's pretty far. So if you haven't used GDB yet and you run it for this code, you're able to use it in your classes. You really should be doing this instead of doing like print debugging. I'm sure every person is like, don't print. But I get it. GDB is confusing. Yeah, the basic thing is that you can run the program with the ability to pause or set up a breakpoint on a specific instruction or specific function call or all those different areas where you can have the program pause. And when it pauses, you're able to inspect the registers of the program, the stack, the heap, and basically see what's going on at this part of the program execution. Which is why you could see like Professor Sage use this instead of print debugging, because if you were ever like printing out the state of a variable, what you could have done instead is set a breakpoint and then inspect the state of that variable directly. And then if you need to get a different variable, you can do it without having to recompile. So yeah, that's why your professors will try to get you to use this. But it's complicated, like there's a lot of different commands you can see, and all of them are very confusing. So again, I'm not going to explain every single command on this cheat sheet. I recommend that you go back to it while you're solving challenges and see what's going on. All right. Again, PwDebug is just a helper for GDB that makes it significantly more useful for the strict binaries we're talking about, binaries without debugging symbols. GDB can actually be incredibly frustrating to use when you don't have debugging symbols. PwDebug helps a little bit. And it just generally helps when you're doing reverse engineering specifically rather than debugging a program. And again, here's some more commands that you can reference. And if you're a Mac user, you might want to look on these slides on how to get Docker running. If you just need GDB, you can run just these two commands in your terminal, the Docker pull and the Docker run, and then that'll get you into a command line interface for an Ubuntu machine that has GDB installed, phone tools, a couple other things. And then that'll let you can use curl-o and then the file URL for the binary to get it into your Docker. And then you can run the chomps directly from there. And that'll let you use GDB on programs that are for x86-64 and for Linux. On Windows, if you're running WSL, you probably won't even have to do any of this. You don't have to use Docker, you can just use WSL directly, use GDB. It'll be a much easier time. But the top instructions only works for GDB. It doesn't include PwDebug, so you either have to install PwDebug in that Docker container, or if you want to have an easier time, you can just go to this GitHub repo. It explains how to do it. All right, I'm gonna walk through one of our challenges. I think this gives you a good glimpse at how to use Ghidra and GDB together to reverse engineer a program. So, I mean, did you open Ghidra? And
Yeah. Just the first test. And. Oh yeah, press the Windows space.
Wait, what?
Windows space to switch it to 40.
Oh, is it okay?
Yeah, actually, if you click the E and G at the bottom right, then click, yeah.
Oh, really?
Wait, you have a different keyboard?
Try just pressing enter. Sometimes it doesn't show up. Then yeah, it'll go.
All right. Ghidra's fighting. Oh. It's gone. So yeah, this is the debugger challenge on PwCTF. You can download it locally and follow along. There we go. This line,
There's a little node, yeah.
I think
You,
this,
you used heater before.
yeah.
That's crazy.
Yeah, okay, so now you can see what I mean by this pseudo C-like output. Like C does not have an undefined for type. So that's just Ghidra saying like we don't know what this is. And also if you've ever written any C code before, you know the main function does not return undefined for. We actually do know the type. So Ghidra lets you read type return, so I know this is going to be an int. So I can just tell it that it's going to return an int. And then also, you know, the first two parameters for the main function, you know, is and what they are and what the types are. Real quick. Main function in any C program. Yeah. Int, and then what's the first parameter name usually? It's RC. And the second one is almost always char pointer pointer. And then RV. Char. So yeah, either lets you retype and rename variables, which will be super convenient because reading programs with all these random variable names can get pretty confusing pretty quickly. So let's see. Now we know we have this argv and it's getting the stir length of it. So I'm guessing like argv1 is going to be this flag parameter to the program. So this is just the length of the flag that we submit. So I'll call it like flag. That's not underscore. Flag length. And then the first thing it does is it checks if it's equal to 0x15. Usually lets you change from hex to decimal, so I can see the flag length is going to be 21 characters. So just by opening it in Ghidra and doing some very basic analysis, we figured out that this program only accepts flags that are 21 characters in length, and it rejects all the other ones. So that's some pretty key information we got very quickly. Now we can see we have this big array of things, and then a for loop. Oops, okay, this is the same 21 times. So this is kind of like in a normal for loop, this would be typed like I. So I'm gonna rename it to I. And now we have something that looks like a normal for loop now. So we see there's the stir compare that's checking. What is this local? This local 18 is just argv again. So we can call it argv copy. And this is just argc, so I'm gonna rename it argc copy so I can remember what it is. Right. So this is again just checking with our flag submission. It's checking 21 characters and it's comparing it to this thing here. And I get any idea what this thing is? Well, I see this for loop is continuously reassigning to this local 40 array, but there's an offset of 8. And because of the way this program is structured, like why is it starting with defining index 8 and then it goes back and doing 0, 1, 2, 3, 4, 1 through 7? So this kind of makes me think this probably is 2 arrays that Ghidra is getting confused and reading as 1. So you can split it back into 2 arrays by saying, instead of this being a bytes 40, I think this is a byte 8. So just 8 bytes. And then I think this is 21 bytes. You can see the 0x14. I'm just going to rename this unknown 1. I'm going to rename this unknown 2. So, wow, look where we started and look where we're at now. Like, this is way more readable. Now it kind of just looks like a normal for loop and then a stir compare at the end. So I don't actually know what this thing is. Like unknown 1 gets transformed and then interpreted as a chart pointer. Like it's doing something to this unknown 1 based on unknown 1 and unknown 2. And then we have this this and here, which again, this and 7 is making me think So let's see. I see this bitwise end, so my first instinct is let's look at it in binary. And I see 3 1s, so that's making me think of the modulo, say on modulo 8. So, and that makes sense because this unknown 2 has only 8 values. But again, I don't really know what the result of unknown 1 is, but what I do know from the stir compare, oops, that no. So what I do know from the stir compare is that this is the flag, because it compares it with my input, and if if the stir compare returns true, then the flag is correct. So what do I do now? Like I could either copy all of this into a new C program and then run it and then figure out what the result of unknown 1 is, or we can use GDB to do dynamic analysis on it. So that's what I'm actually going to go with. Is GDB, do you have the?
I didn't see the.
Okay, you gotta do it. The challenge is called debugger because we're recommending you to use GDB to use a debugger to figure out this value unknown 1, this thing that's getting compared with my input. So while we're waiting, again, you can see that like unknown 1 doesn't depend on your input at all. So even if I type in garbage, as long as I set a breakpoint at the stir and compare line and then see what values gets called with it to figure out the value unknown 1, I'll be able to figure out exactly what the flag is. Okay, it doesn't matter. I don't even have to have like a close guess or a guess that matches a certain number of characters. It can be completely wrong every single character as long as the first 21 are right. Because again, they check that the flag length is 21. If it's not, then you just fail automatically and you don't even get to that line. All right, well, I just ran out. So yeah, we can try and input like a SIGPwny test. And so it's wrong. So we got to use GDB.
Do you want to use the normal GDB, do GDB does because I have GDB heaviest funny look.
That's fine.
Okay.
I'll make it easier, to be honest. I'm typing with one hand. I apologize if it's slow. All right, so GDB, if you want to run it, you just type R and then you put the arguments next. So we want so whatever for flag. Again, you can see it says the flag is incorrect. So let's use a GDB command. So this disassembles the main function, and then this kind of looks like what we're looking at in GDB here, or not GDB, sorry, Idra. But the call we were interested in is the stir and compare call right here, which is 252 instructions from the start. So you can set a breakpoint with this command right here, and this is included in the cheat sheet if you forget ever, and then 252. All right, so now let's run and let's make sure that we provide 21 characters. So let's count out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And remember, we have to provide 21, otherwise we won't even get to the stir and compare call. It will just fail. And we hit our breakpoint, cool. And as you can see, the flag is right there in RDI, which is the first argument. So there we go. All right, so yeah, let's go back to the slides. This is basically the end. So yeah, just go start solving challenges for yourself. If you find any of this difficult, that's understandable. We're kind of going through a lot of stuff at once, but like the real prerequisites to do this super well would be to know systems programming, x86 assembly, C, and then also how to use Ghidra and GDB. Like that's a lot of prerequisite knowledge to learn at once. I think the best way to learn all those things is just by doing the reverse engineering challenges and just trying things out. So again, go solve challenges, but don't be frustrated with yourself if you find things hard. you'll learn more and more as you take classes at UAUC, and you'll learn more and more just by doing these challenges. So, and feel free at any point to ask for help, even if it's just with something like installing Ghidra. I know that can be tough, especially if you're on Mac. So feel free to ask any questions here. We have helpers exclusively to help you out. And for next meetings, again, tomorrow we have our pizza and game night social come out. We're gonna be in 2406 at 7 p.m. And then we're moving to 2405 at 8 for pizza. So I'll make it there tomorrow. And then the Sunday, we're gonna have Pwn 1. Since you came to this meeting, you're gonna be super well prepared to learn about Pwn. I think a lot of people find this to be like the most interesting part of CTFs. Definitely one of the most difficult, which is why we have all of these prerequisite meetings to get there. But you're gonna learn about binary exploitation, you're gonna learn about Stack Overflows, you're gonna learn about overwriting return addresses, and it's gonna be on the path. And then finally, Crypto 1 next Thursday, we're gonna touch on the basics of cryptography. I know a lot of people like that from fall PTFs, so you're gonna learn the basics of that in a mathy sense. And here's the meeting flag again. All right, thank you.